now, when the 88, I don't know, so one of the problems I have is I never know what our marketing names for our chips are. I know what they're called internally. So when the G80 came out, things changed and we added another stage. And by the time G80 came out, GPUs were actually getting fairly complex. These were all very general purpose stages. And each one of these stages could access pretty much any kind of texture resource and be arbitrarily long and do an arbitrarily large amount of work. But they're still part of kind of a fixed graphics pipeline that you're going to go through each of these stages, and there's a little bit of specialization in the hardware for dealing with these different things. Like, coming out of this stage, it's going to feed into here, and out of here, for certain, it's going to have fixed function hardware for clipping and rasterization. And anything that's still colored, we still have fixed function for, right? Now we keep adding more kind of special purpose shaders. So Fermi, which is the next generation coming out, has specialized tessellation hardware. So instead of having to have these insanely complex models that take up who knows how much, where you've specified a really fine-grained mesh, you can just send down control points basically to the GPU now. The GPU will extrapolate from those control points, or tessellate it rather, to get a much more detailed model. And the GPU is getting more complex as time goes by. In a way that's generalizing. Back in 2003, if you asked hardware engineers, they would have said, "Oh my God, going to a unified general shader architecture is a nightmare. That's why we're fast and CPUs are slow. We can't do that." But there was so much pressure to do it, it eventually happened. And the pressure, in a lot of ways, was GPU, and I'll talk about that later. But that's general purpose GPU computing, and people were doing crazy things with the graphics pipeline to get general purpose computation working. And I'll talk a little bit about what people were doing, but it made it obvious that we have a stupid amount of horsepower that you can use, but to shoehorn that into a graphics pipeline was very hard. And the only way to kind of open that up was to unify the shader architectures so that you can use the exact same hardware for doing vertex shading, the exact same hardware for doing geometry shading, and for pixel shading. So this is essentially kind of what our hardware looks like today. I mean, at the very coarsest level, we take an input buffer, run it through our generalized shader core, and that spits out an output buffer. That output buffer then becomes the input buffer for the next stage, and we just iterate with the core streaming multiprocessor. And we, for each one of these passes, we set up the streaming multiprocessor a little bit differently, and run it through here. Some of you guys may have heard, maybe not have heard, there was a lot of work done in the mid-2000s in Stanford on streaming GPU computing, Brook computing, stuff like that. And this was kind of the core idea behind a lot of that, that you have a stream that you basically set up that the data follows through. And the idea is throughput. You want a lot of throughput, and this is the way it's achieved in a modern GPU. And essentially, you can think of each one of these runs through as a thread. And we'll elaborate more on that when we get to CUDA. But this is basically what a G80 level architecture looks like. So kind of an important point is the thread issue. What we're saying here is that the host is kind of like the front end of the chip. It receives all the interesting programming from the CPU and figures out how to distribute that around the GPU. So we get instructions basically saying, I've set up all the state, host handles that, passes it on to the 3D engine, now render. Input assembler takes all of the various data that we've set in state, pulls it together, passes on the vertex thread issue, which will set up the cores for doing vertex work, loading the shader, everything like that, and sends it through. These are labeled SP. Basically, each one of these is a SM, or what we call a stream multiprocessor. All of these cores together in the SM are going to be doing basically the same work. And with G80 level architecture, all of these SMs are going to basically be doing the same work, but not lockstep. That's kind of an important point. In previous parallel architectures, every one of these little green cores all across the machine would be working in lockstep. Each one gets the same operation, but works on different data. So you can do a ton of operations on a ton of data, but it's the exact same operation on every chunk of data. Now with this, each one of these is semi-independent. So these will all pretty much take a branch together. But this one is capable of taking different branches than this one. So that's a big step forward. And also, you can see down here, we've got texture fetch and L1 cache, L2 cache down here, and kind of a specialized texture cache. I'll talk a lot more about caches later, but having a specialized texture fetch unit basically lets you do all sorts of texture-specific computations, interpolation, prefetching, address calculation for the textures, stuff like that this doesn't have to think about. So it's something that a CPU kind of sort of has, but not anywhere near as specialized, and this is much faster than trying to do it in a general purpose way. And the cache is really critical for performance. Just as much so as a CPU, and I'll talk about caching more later, so I don't want to belabor it here. But kind of the important point with this slide is that it feeds around into itself. So kind of each pass through will feed back in through a later pass, and eventually, presumably one of the final passes with Pixel will pass it out to some specialized compositing hardware and then to the frame buffer. So this is a somewhat more modern architecture, GT200 based. I think this would be a 285 level board that our marketing calls it. Forgive me if I'm wrong. But you can basically see that things are centering a lot more around the cache now. And the way things are issued and handled, it's more complex. And a lot of the layout of the chips now is really centered around memory. And we'll get to why that is. But I'm talking a lot right now about the computing resources, but the actual underlying memory for this and how we manage the memory is key. If you neglect, in your programming as well, if you neglect the memory aspect of it and focus on just the computational aspect of it, you'll get some performance increases. But using the memory properly is where you get massive performance increases. And you can't really get one without the other. If you have a really great memory architecture without the computing part, well, I'm sorry, you're not going to get it. But you have to have both together. And one really key thing when you're programming, by the way, this slide looks different from every other one because this is one I cooked up, so it looks bad. But obviously, this is simplified, like really simplified from the way things look in the real world. But the CPU has to go through the system caches before it can get to system DRAM. And this is a really insanely fast bus. I mean, essentially, this is on the same chip. And the CPU would be molasses slow if it didn't have this. I mean, I can't emphasize how important the cache is, but this is, in some ways, everything. And then when the cache fails to do its job, which it can't be perfect, you fall back to system DRAM. And then that's a really slow operation. So if that's a slow operation, and this is an insanely wide and fast bus, imagine how slow this operation is. So anytime the CPU and the GPU are talking and transferring data back and forth, it's inherently slow. I mean, yeah, PCI Express 2.0 or 3.0 or 10.0, whatever we're on now, it's not that fast, not compared to the internal buses that the chips use. And so one of the things that is really tough in GPU, or any sort of compute where you're using different chips, is using your memory smartly. You don't